Hello everyone. So welcome to the digital event series of ISTVS event series before the as a build up to the conference of ISTVS, the 20th International Conference later this year. So before we begin, I just wanted to welcome all of you and ask everyone to introduce yourself in the session chat. We so that we can informally get to know each other. Beyond that, uh, during the during the course of the presentation, we request that any questions be directed through the sessions Q&A tab. And also, after the end of the presentation itself, we also will be asking people to join to the session live by pressing the share audio and video button so that we can have a real-time discussion with each other. So our guest for today is Professor Schalk Els, the head of the Vehicle Dynamics Group of the University of Pretoria. Professor Els completed his doctoral studies at the University of Pretoria. He's currently the Deputy General Secretary of ISTVS for the Europe Africa regions, and also he is an editor of the Journal of Terramechanics. He has also been a co-PI of the ISTVS project, in which a team worked collaboratively to update the standards of the ISTVS. He will be discussing his insights on the topic of off-road vehicle dynamics today. So without further waiting for it, I would go ahead and request Dr. Els to uh, like, share his insights.
Thank you, Mohit. Thank you for this opportunity. I must put a disclaimer out there. It's the first time in this series that we're actually having a presentation with lots of videos. So I like showing lots of videos. I did pre-record my PowerPoint, so I'm just going to play the pre-recording. But if you have any problems with sound or video, please let us know in the chat. We'll try from our side to fix it. Part of this digital event series purpose is to figure out how this platform works so that we can have our nice conference in September. So if we have technical glitches now, there are people behind the scenes who can help sorting out these technical glitches. So I'm going to share my presentation, and afterwards there will be ample opportunity for questions. Please use the Q&A button on your screen if you want to post questions as the presentation goes. In our group, we are looking at the dynamics of vehicles of different types and sizes, from very small vehicles, as you can see in the middle bottom. Good morning, good afternoon, good evening, everybody. My name is Schalk Els. I am the research group leader of the Vehicle Dynamics Group at the University of Pretoria in South Africa. My talk today will be about off-road vehicle dynamics. In our group, we are looking at the dynamics of vehicles of different types and sizes, from very small vehicles, as you can see in the middle bottom, a bar SAE, a vehicle weighing 350 kilograms, including the mass of a driver, up to all the way to very large mining vehicles driving on mine ore roads that can carry up to 350,000 kilograms of ore or rock in this case. And then a lot of work on sports utilities vehicles, such as the Land Rover vehicle you see in the left bottom corner of the slide. Now, the picture we're looking at is a very simple picture. Basically, the vehicle drives over the terrain, and the vehicle is in contact with the terrain through the tires. So the tire-terrain interaction is where all the external forces are applied to the vehicle if we neglect aerodynamics. It is also the area of special interest for the terramechanics community and the off-road vehicle community. So we need to understand the terrain tire interface and how those forces are generated. Then the forces are applied to the vehicle through the suspension system. And the suspension system usually consists of linkages, but also springs and dampers. And the reason for the suspension system on the vehicle is to actually manipulate the vehicle dynamics so that the human driving the vehicle or sitting in the vehicle is kept comfortable and safe. So this is the basic picture that we need to understand in order to analyze and model the dynamics of off-road vehicles. So we start with the terrain profile. This picture shows you a mechanical profilometer, which we call the can-can machine. It has lots of legs, lots of bent arms. These arms follow the terrain and we measure the angle of these arms. And in doing so, we are able to accurately capture the vertical versus longitudinal profile of the terrain at a certain lateral spacing. So a very nice way of getting the profile of rough terrain. And I should emphasize here that this is especially designed for very rough terrain with large obstacles that we need for off-road vehicles. Then next in line, after we understand the terrain, is the tires and especially the enveloping effect. So here you can see a large agricultural tire on a static test rig. The white lines on the tire used to be straight lines when the tire was not compressed, but now we compress the tire against a square tubing cleat. So that's an obstacle against which we compress the tire. And now you can see that these initially straight lines are now very curved, giving us an idea of how much the tire actually deflects around these obstacles. We also built a dynamic tire test trailer. Here you can see our tire test trailer. The tire here in the middle is the tire that we are actually testing. The other tire here is just a stabilizing axle. We can use this equipment on any terrain as long as we have a towing vehicle capable of towing this tire test trailer over that specific terrain. Here's an example of a small passenger car tire where we just do a longitudinal force versus slip test. So we simply tow the vehicle at a speed and then we brake the tire. If we do this on very large tires, you'll now see our tire test trailer. Again, the two rear axles are now only for stabilizing purposes, but the wheel in the front here is the wheel we actually test. So we apply a slip angle to this tire, as you can see, and then we slowly brake the tire until it locks up. So at the lockup point, we release the brakes. We adjust the slip angle using a slip angle actuator until we reach a new slip angle, and we repeat this process. So we can do this on tires up to 2.1 meters in diameter and 5,000 kilograms vertical force. The forces between the tire and the tire test trailer are measured with a 6-component wheel force transducer, so we get longitudinal, lateral, vertical force, as well as the 3 associated moments, measured directly using this wheel force transducer. You'll also see how the stiffness of the tire changes as we basically lock the tire. So a very powerful piece of test equipment to test large tires on different terrains, different surfaces where we want to get tire characteristics. We can also perform abuse cases on this test trailer. So here we're running the tire at a fairly high speed with a constant slip angle, and the friction generates heat, and you can see the effect of this on the wear of the tire. So this is something you cannot do normally on vehicles while driving, because the vehicle would have rolled over long before you could reach these abuse case applications. We also measure motion resistance. Now this picture may look a little bit strange to you because we have this massive tire at very high load and we tow it with this very light sport utility vehicle. But the reason for this is that we connect the vehicle to the trailer with a very sensitive load cell. Load cell that has a full-scale range of about 500 kilograms, which means that we can measure the rolling resistance force. And the rolling resistance force opposes motion, but it's usually less than 1% of a vertical force on the tire. So we really need to be able to measure very accurately. It also means that the axle position on this trailer can be adjusted so that the center of mass of a trailer is above the wheel contact position, eliminating most of the vertical load on this very sensitive tow bar load cell. I alluded to wheel force transducers before. Wheel force transducers are very expensive pieces of equipment, and we embarked on making our own. So these 4 ranges of wheel force transducers are all in-house designed and manufactured by the Vehicle Dynamics Group. They vary from a small transducer for a typical 10-inch rim, small all-terrain vehicle, quad bike type application. We have a passenger car sized wheel force transducer that will fit into 16-inch rims above. And we have a 20-inch wheel force transducer designed for the typical truck and off-road applications, and also a very large 29-inch version, which is capable of carrying 300 kilonewtons or 30,000 kilograms of vertical load at 50 kilometers per hour. Still on the topic of tire-terrain interaction, and especially coming towards the softer terrain, which is Terramechanics, is this system which we call the T2CAM system. It's short for Tire Terrain Camera System. What we basically do here is we have 2 digital cameras mounted inside the tire. So these cameras sit inside the air cavity of a tire, and as the tire rotates, these cameras face the contact patch area of the tire. And we can then use digital image correlation techniques to get the 3-dimensional deformation of the inside carcass of the tire. You'll also see that this is coupled with a wheel force transducer measuring all 6 force and moment components. So in theory, having deformation and forces can enable us to calculate stiffness. Of course, very complex stiffness, but it allows us to get a very much bigger, deeper understanding of what actually happens between the tire and the terrain. So in this case, you can see the tire traveling over the trapezoidal bump in such a way that only half of the tire is on the trapezoidal bump. And the image at the bottom that rotates now shows us free analysis where the tire just starts contacting the bump, where the tire is on top of the bump, and where the tire leaves the bump. And you can clearly see the areas in blue where the tire is compressed, and the area in red where the tire is extended as it hangs off the side of a trapezoidal bump. So this gives you an idea of the 3-dimensional displacement measurement we can get in the contact patch. We can do this dynamically. So this is a vehicle performing a slalom test on a muddy, icy gravel road. This is the inside of a tire on the right-hand side, and you can see not only how the tire sidewall flexes left and right, but you can also see the obstacles in the tread of the tire. So the terrain over which we drive is not smooth. So we have this 3-dimensional deformation picture coupled to a full force and moment picture on the tire. We also use the same digital image correlation technology using 2 cameras, but we can now use that to measure rut depth, for example. So the photo left top shows you a picture of a tire tread pattern left in snow, and the picture at the bottom now shows you the digital image correlation where we actually have a 3-dimensional profile of this rut with a scale so that we know the exact depth of a rut left by the tire. So this is an example of a braking test on ice, very slippery conditions. The vehicle accelerates and then brakes, but you simply lock the wheels, the vehicle skids to a standstill. In this case, we also use digital image correlation to measure slip and slip angle and other vehicle parameters. One of the big problems with the types of vehicles that we're working on, namely off-road vehicles, is that they also require good on-road performance. And many off-road vehicles have soft suspension systems and high centers of mass, which means that they are susceptible to rollover. So this is a test we witnessed many years ago where this vehicle was tested for a double line change. The driver applied too excessive steering angle and the vehicle physically rolled onto its side. Mainly due to soft suspension combined with a high center of mass. Severe problem in many of these types of vehicles. So part of that solution is working on suspension characteristics. Now the problem is that once you have the suspension characteristics required for good off-road ride comfort, meaning large suspension travel, fairly soft springs and low damping, you have on-road stability and handling problems. If you now design the suspension system for good on-road handling and stability, then the off-road driving capability of the vehicle suffers. So for those purposes, semi-active or active suspension systems have become popular. So this is our version of what we call a 4S4 or 4-state semi-active suspension system. This system contains 2 gas accumulators that are separated by a valve. This means if a valve is closed, we compress the gas in a small accumulator, therefore resulting in a stiff spring for handling purposes. If we open this valve, we combine both gas accumulators. We have a very large gas volume, giving us a soft spring characteristic for good comfort. We do the same with a damper. We add a bypass valve to the damper. If a bypass valve is closed, all the flow goes through the normal damper pack, which means we have high damping for good handling. If we open the bypass valve, most of the flow will bypass the damper, giving us low damping, which is required for good ride comfort. So in this semi-active hydropneumatic suspension system, we can have a setting for good on-road handling and stability, but we can have another setting for good off-road comfort and large wheel travel, and we can switch between these 2 settings in less than 100 milliseconds to change the suspension system between ride comfort mode and handling mode. Now, if we apply that to the vehicle, you'll see this is the same double line change showed you before. Again, the driver loses control over the vehicle, but the vehicle doesn't roll over. The load transfer is high enough, so the vehicle starts sliding, it remains on its wheels, and we prevent the rollover simply by changing the suspension characteristics on the same vehicle. Another big challenge nowadays is the driver, the control system behind the vehicle. So the driver of a vehicle needs to control the speed of the vehicle through the throttle and the gear change. The driver needs to brake the vehicle to slow it down, and the driver needs to apply steering. Now, we all know that humans are error prone, and many accidents are basically caused by the human making some guesses or applying some inputs to the vehicle, which can result in an accident. So the solution past that is very widely known now, and that is autonomous driving. So in this case, you can see that same test vehicle again performing a double lane change, but the driver actually have to drive the vehicle. The vehicle drives itself using sensors and control algorithms. The challenge with off-road vehicles, however, are that these control strategies must be able to adapt to the conditions. The roads may be rough, there may be a lot of dust in the environment, so adaptive controls are required that can actually handle a very wide range of on-road and off-road driving conditions, such as you can see in this double line change on the gravel road. One of the things VDG does on a continuous basis is international collaboration. This slide shows you the consortium for Project EVE, which was funded by the European Union under Horizon 2020. And you'll see that we worked, in this case, with a large variety of partners from Germany, the Netherlands, Belgium, South Africa, the USA, all in this area of integrated chassis control systems for this specific project. So we are very well versed and capable of working with large consortia of international research partners. This slide shows a slalom test performed by a vehicle on slippery, muddy terrain. In this case, one of the big difficult things to measure under these conditions is the actual slip angle of a vehicle. So we use digital image correlation. Again, you'll see that there are cameras mounted to the side of the vehicle, and these cameras basically face downwards towards the terrain. And by using digital image correlation, we can measure things like vehicle speed, longitudinal vehicle speed, as well as lateral vehicle speed, and the resultant, of course, gives us the side slip angle between the vehicle and the road in which we're driving. One of our more recent research areas is in the field of collision management. So there's lots of similarities between this and autonomous driving, except that these collision management systems are designed specifically for mines, and they are designed to prevent collisions between very large off-road vehicles. In this case, you can see two heavy dump trucks, and we are doing a lot of work for the mines in South Africa in order to implement these systems to reduce collisions or avoid collisions between vehicles. These vehicles are very heavy, the dynamics are slow, they can't stop very quickly, they drive on ore roads, which are mostly gravel roads, often wet gravel roads because of dust suppression. So their dynamics are quite slow, they take a long time to accelerate and brake and steer. So therefore, technology is very applicable in helping us to actually keep these vehicles safe and keep them from colliding, especially in conditions where the driver, again, is not in a position to make a suitable decision. So in general, vehicle dynamics picture for off-road vehicles will now be illustrated in terms of a short example where we developed ABS, anti-lock braking systems. So we took a test vehicle with ABS fitted, did a braking test in a very rough terrain. We measured the profile of that rough terrain using our can-can machine with the arms. So the real-world profile becomes a digital terrain profile. We then characterized the tires and built models for the tires. In here you can see that the tire model will now generate all the vertical, lateral, longitudinal forces as well as the moments associated. Then we'll add the rest of the multi-body vehicle dynamics, so that adds suspension characteristics, springs, dampers, moments of inertia, drivetrain, everything we need, as well as the control system for the ABS. We then simulate the ABS braking system on this rough terrain and calibrate back to the tests we performed. And then we use this model to now change either the suspension system or the control algorithm parameters until we find a better solution for the specific off-road driving problem, in this case, ABS braking on a rough terrain. So that is a short summary of what the Vehicle Dynamics Group at the University of Pretoria typically does. This is our bar SAE team performing a jump on the small self-designed, self-manufactured vehicle. And we believe that in everything we do, we try to take vehicle dynamics of off-road vehicles to new heights. Thank you, and you're welcome to ask questions.
Thank you, Professor Els. Now, I've seen that we have a couple of questions in the Q&A tab. If you would like to answer them, I can read them out, but we would appreciate it if people joined the call live and had a detailed discussion. If anyone who would like to join the call live, it can please press the blue colored share audio and video button, we can have a detailed discussion of questions as well as viewpoints, various viewpoints.
Thank you, Mohit. I will start with some of the questions. In the meantime, if people have other questions, they can find the correct button. Apologies for me struggling for the first few minutes because there are really many buttons to press, much more than I expected. But I hope everything worked out in the end. So the first question is on the tire terrain camera system, and the question is, how are the cameras installed inside the tire safely? So there's a whole mechanical mechanism that basically connects the cameras to the rim, also to the outside, because you must remember we must have these cameras pointed at the contact patch. The cameras cannot rotate with the tire. So there's a whole ring gear and planetary gear system that does that. Of course, the cameras need to be mounted far away from the contact patch. So if you drive over an obstacle, but you don't actually hit the cameras. So the cameras are therefore towards the side at an angle. We also have a new arrangement now where the cameras are actually opposing each other. So yes, it's a very delicate system. It's not for installing on a vehicle and then going crazy. It's a sensitive scientific measurement instrument. But as long as you control your tests, you can get extremely good data out of this. The second question related to that is, can you give an example of how the data from inside is used? So there are many ideas that we are working on one by one at the moment. One of the first things is, if you work in the terramechanics field and you want to calculate slip, you do a drawbar pull versus slip test, for example. In that slip calculation, we assume that the radius of a tire is the deformed radius on a hard surface. We make some kind of assumption on V equals R omega, meaning we measure the vehicle speed, we measure the wheel angular speed, and using some definition of radius, we calculate slip. Now, if a tire now sinks into the road and there's three-dimensional deformation, that assumption of a constant rolling radius is not a good assumption anymore. So we can, for example, use the three-dimensional measurement inside the tire to get this non-constant radius as the tire is moving through this terrain. The other kind of thing you can get is, if you measure the lateral force and you measure the lateral deformation of a tread, you can get an idea of lateral stiffness. So there's a lot of these things that we are exploring. One of our latest endeavors is to build an inverse finite element analysis, where we apply the displacements to the inside of the tire and then try and calculate the forces, distributed forces on the outside of the tire. So that is work in progress with some promising results, but it means this can lead to what is called a smart tire. The camera data may provide data on the forces and moments that the tire generates. And that, of course, has many, many advantages in vehicle dynamics control systems. So we have not explored the possibilities of T2CAM nearly to its full extent. We have a very nice measurement system, but there's lots of research that can be done. There's another question on the side slip angle measurement, and the question is, how well does our system compare to commercial systems? We've done extensive benchmarking against the commercial system available, and we found that the commercial systems are generally made for high-speed driving on fairly smooth roads. Our system excels at the low speeds below 15 or 20 kilometers per hour, typically the speed you get during terramechanics or the kind of applications I showed you where the road is very soft and slippery. So there our system outperforms the commercial system by a significant margin. It's also much less sensitive to the terrain roughness. So we found that the commercial systems do not perform well if the terrain is rough. So as soon as the sensor starts moving up and down significantly, the quality of a slip angle measurement from the commercial systems degraded substantially, while because we use the two cameras, the height change effect is virtually cancelled out. So under the Terramechanics, fairly low speed, rough terrain, off-road conditions, our system really gives excellent results. Okay, any other questions?
Thank you. We'd like to invite all our attendees if they can join the call.
Can I ask a question?
Sure.
Prof. Els, you alluded initially to the suspension system having different damping and spring characteristics that can be useful for different handling or performance tests in general. And then you also showed the videos of the braking on rough terrains. Have you found any correlation between the suspension settings that you can change and the braking distance that you can improve?
Yeah, so it turns out that the rough terrain has a significant effect on the forces that the tire can generate. If the terrain is very rough, the tire often loses contact with the ground. So if the tire is not in contact with the road, then obviously there are no forces between the tire and the road. So that's where the suspension system plays an enormously important role in order to try and keep the wheel, or the so-called unsprung mass of the vehicle, to control the unsprung mass and keep the tire in contact with the ground. So we also found that under those braking conditions, there's a significant difference between the characteristics you require on the front suspension of a vehicle compared to the rear suspension of a vehicle, simply due to the load transfer that occurs during braking. So yes, the short answer is suspension characteristics are extremely important for braking on rough terrain, much more so than for braking on normal roads where the terrain input is small.
Thank you.
Any other questions? So there's a question with regards to the four-state semi-active suspension system. How quickly does the system change characteristics? So the system I showed you has normal hydraulic solenoid valves, and the response time is between 50 milliseconds and 100 milliseconds. So we can change between the ride comfort and handling mode between 10 and 20 times per second. So it's not extremely fast as you will have with a fully active suspension system, but in terms of vehicle dynamics, changing between the ride comfort and handling mode, it's actually a very, very fast, very quick to change the characteristics. So it's not fast enough, for example, to implement the normal, the skyhook or ground hook type strategies, but it's definitely fast enough to adapt to various terrain or driving conditions.
I had a question, Professor Els. So earlier during the presentation, there was an image in which you showed like digital image profiling of a like rut in snow. So in
Yes.
such a case, I was just curious, like how were the tests conducted, and especially like how were the cameras mounted?
Okay, so we basically have.
If it leaves a snow trail or something, does it affect the camera? Or
So
you just
that's a very interesting question. So the cameras face downwards, vertically downwards towards the terrain. And because of the fact that any objects flying through the image will be visible in both cameras, we can actually, it actually doesn't influence the measurement that much. So we found it to be insensitive to mud or vegetation or debris flying through the camera's field of view.
Thank you.
So you'll see we do a lot of work with cameras. The idea at the end of the day is to we can measure velocities and angles and orientation, displacements. We can even measure strain with cameras. So I haven't showed any slides on the strain measurement, but we can take the T2 cam system and measure strain on the rubber itself inside the tire. So the whole idea is that we mount cameras in front of the tire, which will give us the undeformed terrain. We mount cameras behind the tire, which will give us the deformed terrain, so the rut in 3 dimensions. We mount cameras inside the tire, which will give us the deformation in 3 dimensions of the inside carcass of the tire. And then the idea is if we can substitute or superimpose the tire carcass dimensions onto the inside measurement, we should be able to get the outside measurement of the tire. So that gives us a three-dimensional volume change in the soil as it starts from undeformed through the tire to deformed after the tire. And together with that, we can now measure speed, slip angle. If you add a wheel force transducer to the tire, you can get all the forces and moments as well. So from a terramechanics point of view, it's a dream of a measurement system. You can get almost everything you can dream of. The question now is how do you use the information to take the research forward? So I would like to invite people that are listening, if you're interested in this topic and you're thinking of collaboration or talking to us in more detail, yes, please contact us. We're always willing to talk to people. There are possibilities for exchanging students. There are even postdoctoral opportunities that we can explore. So yes, people interested, please contact us. So there's a question, since you're always dealing with small sample sizes, how do you control for consistency or variability in tires? Okay, so that's a very interesting question, but I think the context is important. So how finely or how accurately do you want to measure, and how accurately can you control your conditions? So let's say you drive in soft soil and you can measure the tire deformation with sub-millimeter accuracy, but the soil properties can vary by 20 or 30%. It's a question of which values do you believe more, and doing uncertainty analysis to interpret your results at the end of the day. The one benefit of these systems is that we can, to a large extent, automate at least part of the data acquisitioning process. So normally, if you would do a test in soft terrain, the rut profile measurement would be a manual process. So you would physically go with a stick and a ruler and you would physically measure a certain number of points. In this case, we have video images that we can process, and we can, for example, then extract a graph of rut depth versus time or versus distance. So the variability in tires itself is also a good question. We've done investigations where we looked at the effect of wear on tires. We also looked at the effect of age, because the rubber changes properties with time and with temperature, ozone damage, things like that. We found most of those things to be quite small effects, especially on passenger car tires. We just completed a study on agricultural tires where the effect of wear is enormous. There's a huge difference between a new agricultural tire and one where the tread has been worn away. So that is those results are in process, where I hope to submit those papers in the next week or two. But some really interesting results on how much wear and those kinds of things, terrain, actually influence tire properties. So there's a question, have you evaluated how well your rotating drum tests work compared to the vertical variation or ground level surface profiles for inducing wheel vibrations or oscillations? So our drum is simply a smooth drum. We haven't done drum tests with cleats or obstacles on drums. The square tubing cleat I showed you is on a static test rig, which can apply displacements in 3 directions to the tire. So we do not actually have dynamic drum test applications, but what we do know is you have to be very careful in terms of how you interpret boundary conditions. So let's say you press a tire against the drum and you have an obstacle, a cleat mounted on the drum. The boundary condition that you impose is that the distance between the center of the tire and the drum stays constant. In a vehicle, it's not the case. So if you do a field test where you drive that tire over the obstacle, the center of the tire will actually move up and down. So the boundary condition is not a fixed distance boundary condition now, it's a force boundary condition. So it is really important when you compare different methods or different techniques for obtaining parameters that you realize the boundary conditions are not the same. So you cannot expect the same results. You have to compensate for the fact that in the one case you have displacement control, if you want to call it that, in the other place you have inertia or force control. So the difference between static or non-rolling stiffness and dynamic or rolling stiffness on tires have been known for a very long time. So you cannot compare the measurements on a static tire with that on a rolling tire. Tires are extremely complex, and there's still a lot of things that we don't really fully understand yet. What I haven't shown you is that we do have a damping test trailer, which is another test trailer but without any suspension. So the axle is rigidly mounted to the trailer. And because of that, we can simplify the trailer as a rigid body and a pendulum. So we use that to obtain dynamic stiffness. So we would tow that tire test trailer over cleats or bumps or rough terrain and then measure the response. So in that case, at least we do not have the effect of a suspension system. The boundary condition is therefore much easier to actually quantify. If you are using a vehicle or our large tire test trailer that has suspension on it, then the suspension, of course, also influences the boundary condition. Makes it much more difficult to do transient tests. Good. Anybody else?
So it looks like we do not have any more questions. If people on the live session, if they are still interested in joining the call and posing a live question, we are open to it.
Okay, I would encourage you to participate further even after this. The video may be made available as well, I think. So anytime you see this video, if you have more questions or you're interested in some other aspects, I think you all have our contact details. If you don't have mine, just visit istvs.org, the ISTVS website, and you'll find my contact details there, or visit the Journal of Terramechanics website, and you'll find my name under the editors list. So if you have any questions, please feel free to contact us. We also hope to see most of you, if not all of you, at the conference. Of course, it's a virtual conference, so you can sit in your lounge and attend the conference, but we will have lots of interesting things to discuss at the ISTVS conference as well in September.
Thank you, Professor Els. So before we wrap up, we just had some major announcements that had to be made. So just give me 1 second. So as a part of the ongoing digital event series, the full series details and registration links are available on this ISTVS website newswire link. So in this series, as we all know, we are alternating between the Terramechanics Bites, which is like seminars or presentations by research professionals or professors, and student research seminars. So in that chronology, we have a student research seminar next week, which also reminds me we encourage student research groups in various parts of the world if they would like to present their work as a part of the digital event series. It it may not be a complete. As far as the student research seminars are concerned, we are open to having a more informal mm, discussion rather than a presentation. The next Terramechanics Byte event will be presented by Dr. Lutz Richter. He's the first Vice President of ISTVS and Regional Secretary for Western Central Europe. The topic of his talk will be Terramechanics models for lunar and planetary rovers. The event link has already been set up and will be accessible through the website I mentioned earlier. So that event will be on August 25th, although there is a slight change in time. So that one will be 11 a.m. Eastern time, which is 4 p.m. Central European time and 11 p.m. Japanese Standard Time. Also, in addition, the 20th International and 9th Americas Conference of the ISTVS is upcoming and will be held online through the same Hopin platform from 27 to 29 September 2021. The link for registration is available on the conference website, which is conference.istvs.org. So we encourage all our participants to go ahead and register for the conference too. So thank you and see you soon during the next digital event series and hopefully during the conference as well.